Hello, everyone. Okay. Okay, so I hope you can hear me well. I'm going to share my screen and let's get started. As usual, this is not the first webinar on magnetic fields. I've done at least two, I think more than two. And I hope you all know where you can find the last year's recordings. Okay, so yes, so let's talk about magnetic fields. I've covered, well, repeating myself, I covered this topic extensively. I'm going to be slightly repeating myself. Hopefully, you'll find something new. Okay, so let's start. So we start with the cross product of two vectors. So there are two ways in which you can multiply vectors. And the first one was the scalar product. So the dot product, or the scalar product was vector A times vector B. And well, the definition was modulus A times modulus B times cos of the angle between them. And it's called scalar product because the result is a scalar, of course. Now, the cross product is different. Cross product, also known as the vector product. It's A times B. And the easy way to remember it is modulus A times modulus B times sine theta. But of course, that's not true because this is a scalar, clearly. So you have to multiply it by a normal vector, a unit normal vector found using the right hand rule, which is weird. Who has done vector product? Who knows what vector product is? Type 1, please, and 0 if you haven't done dot product before. Okay, so okay, 40-60 split. Okay. Well, yeah, so this element makes it a vector. So this is a scalar, and this is a vector. So what's the deal with the right-hand rule? Suppose you have vector A and you have vector B. You need the vector n would be in such a direction that if you were looking from the top, if you were observing this situation from the top, A would be turning anti-clockwise towards B. Okay. What's the name that we gave it? The normal vector. This is one way of looking at it. Sorry. Okay, so right-hand rule. That's one way of looking at it. So for example, if you open up a coordinate system like x, y, and z. If you were to climb z like a tree, if you were to climb z and sit on top of z, so you are here. You are here looking down. Looking down. Okay, so you're looking down and you see the x-axis and the y-axis. The x-axis has to turn anti-clockwise towards A. The shortest way to turn x to y is anti-clockwise. And this is called a right-hand triplet or right triplet. So this is known as a right triplet of vectors. On the other hand, if you have y and x, and you've climbed z, and you're sitting on the top, you look down, x would be turning clockwise. This is called a left triplet. This is how I remember it. You don't have to use the same method, but I think it's way easier than using the right-hand rule. The right-hand rule, on the other hand, is slightly different. And it's like this. Now, this is vector A, this is vector B, and this is vector N. Well, C is parallel to N, so vector N is this way. Right-hand rule. So if your first finger coincides with you take your right hand, if your first finger coincides with the first vector, the second finger coincides with the second vector, then the thumb will indicate the direction of the vector product. Now thinking of it, that's actually way easier. Does that make sense? Do you understand the logic here? On a scale of 0 to 10, please. Not the rotating thing. So similarly to this, so we use the right triplet. So we use the right triplet. So if we climb vector n, basically how it works, if you have vector A and you have vector B, the cross product will always be perpendicular to both. So there are two possible directions. You can have n like this, or you can have n like this. If you climb n and you look at A, and A turns anti-clockwise towards B, that's the right-hand rule triplet. And the other one is the left-hand rule. Is the normal vector just, yes, 0, 0, 1. So in this case, well, let's do some examples. Example. That would make more sense. Example. Suppose you have the coordinate axes. This is the x, this is the y, and this is the z. And the simplest three vectors that I can think of is I, j, and k. Okay, so I is of course 1, 0, 0. J is of course 0, 1, 0. And k is 0, 0, 1. Okay. Now I want to multiply I multiplied by j. Vector I multiplied by vector j. I'm going to use the definition, this definition of the cross product. A modulus I multiplied by modulus j multiplied by sine of the angle between them and multiplied by the normal vector. So the normal vector is the hardest part. The normal vector found using the right-hand rule. Okay. Well, this is just 1. The modulus of I is 1, multiplied by 1, multiplied by sine 90 degrees, and multiplied by n. So to find n, we use this. And in this case, vector A, the first vector, is I. This is j. And the third vector is up. So if ij, well, what is the unit vector perpendicular to I and j going up? Well, that is k. It's in this direction. It's in this, so the normal vector is going to be 0, 0, 1. So it's vertically up. So it's going to be 0, 0, 1. And in this case, this is 1, 1, 1. So it is just 0, 0, 1, which is just k. So an interesting fact that the cross product of I and j is k. Similarly, you can prove that using similarly I multiplied by k is going to be j, and k multiplied by j, no, j multiplied by k, j multiplied by k is I. Is I. I times k is j. No. K times I. K times I is j, sorry. But if you change them the order, j times k, or j times I is going to be minus k. So it's anti-commutative. That means if you change the order, k times I, k times I, yes, and j times k is j, j times k is I. So I times k is minus j, and k times j is minus I. So it's some interesting facts here. But you can do this using, you can find the cross product using the coordinates. Finding cross product using coordinates. So the easiest way, well, in my opinion, if you have vector A with coordinates A1, A2, A3, and vector B with coordinates B1, B2, B3, then A times B is the determinant of a matrix I, J, K, A1, A2, A3, B1, B2, B3. How do you find the normal vector with the right-hand rule if they have vectors that aren't as simple? If they're not simple, you use the coordinate method. Simple. The simplest way. You use this method. Or you just use a very imaginative coordinate method to find, well, I mean, it has to be perpendicular, right? So the normal vector is perpendicular to A. That means that n times A has to be 0. And it's also n is perpendicular to B. That means n times B is equal to 0. So you can work it out from this. And the modulus of n is equal to 1. So you 3 equations, 3 unknowns. The unknowns in this case would be n. N is equal to x, y, z. So this is how you can do it. Answering your question, how to find so there was a question here. By solving simultaneous equations. So answering your question. Why would it be cross and not dot for the perpendicular? Sorry, of course it's dot. I meant to put cross. I meant to put dot. Sorry. Yeah. So finding cross product. So here you just find the numerator. So let's check this out for I and j. I equals 1, 0, 0, and j is 0, 1, 0. So I times j is equal to I, j, k multiplied by 1, 0, 0, 0, 1, 0 equal to I multiplied by 0 minus 1 plus j multiplied by oh sorry 0 minus 0 silly of me. J is 0 minus 0, 0 minus 0, and it's a minus, but that doesn't really matter, plus k multiplied by 1 minus 0, which is just k, which is 0, 0, 1. Okay. Would you like me to spend another 5 minutes and just do another example multiplying just two random vectors? Or are you happy with, so yes or no? Yes or move on? Please vote in the chat. Yes, I would like to see multiplication of two vectors. On move on to the next question. Okay. All right. Excellent. So problem 2 is almost exactly the same as problem 5 from the assignment, I think. Problem 5 from the assignment. Where is it? Where is my problem 5? Here it is. Yeah. Problem 5, so 6 marks, double star question. At time t, an electron is located at point and is moving with velocity this. A magnetic field is acting along the positive z-axis. Describe the trajectory of the electron. So yeah. So we have a magnetic field, B. And we have the velocity of the electron. Okay. And, okay. So what would we do here? Well, first of all, I try to imagine it. So the magnetic field is 0, 0, 2. So the magnetic field is vertically up. And the electron is moving along the x-axis, along the y-axis, and along the z-axis. So it has a component along the x-axis, it has a component along the y-axis, and it has a component along the z-axis as well. So basically the electron is moving like this, something like this. All right, so it has a component. Okay, I'm not very good at drawing, but I think you understand what I mean. Okay, so it would be useful to look at this example from the tip of the z-axis. So we climb the z-axis like a tree again. We climb at the top and we look at it from the top. So view from above. So you have the magnetic field. Now the x-axis is like this. Axis is like this. The y-axis is like this. And you have the electron. The electron is traveling like this with the velocity, and the speed is 3, 3. So it's 3 along the x and 3 along the y. Okay. Right, so this is the velocity. And using F equals QVB, F equals QVB, we can find the force acting on the electron. The force acting on the electron is, we are only talking about the plane XY. So the speed in the XY plane, we have to exclude the Z direction for now. The velocity in the XY plane is just simply 330, and the speed in the XY plane is going to be square root of 3 times square root of 3, so 3 square root of 2, I believe. Yeah, 3 square root of 2 times 10 to the 6 meters per second. Okay, so the force is perpendicular to the path of the electron. What is the direction? Well, we can find that using the left hand rule. So the first finger is the field, so field is towards me. The middle finger is the direction of the current. So the middle finger is pointing opposite. So current is in the opposite direction. The field is out of the page, off page. Current is that direction. So the force is going to be up. So the force is going to be in that direction. Okay. And of course, as you know, that the force is perpendicular to the velocity. So what would happen is it will go in a circle, because at any point the force would be towards the center of the circle. Right. And you could also say that, well, force is equal to QVB, but it is also equal to mv squared over r, over the radius of the circle. And you can v, so the radius of the circle is mv over qb, where q is the charge of the electron. That's nice. Can you just give me a second, please? Hi. Sorry, it sounded like trick-or-treaters have broken into my house. Okay, so yeah, the radius of the circle, but that's looking from from above. Now, the magnetic field has no effect on a particle moving along the field lines. So in the xy plane, the particle is moving in circles. However, in the z direction, the field has no effect. This is because if you multiply two vectors, f equals qvb, f equals qv times b, if the velocity is in the same direction as the field, then the sine of the angle is 0 degrees. So the modulus of f is going to be qv times b times sine theta, which is 0. What did you use? No, I used the left-hand rule to find the direction of the force. I didn't use. I haven't used V and B. But okay, I can do that. Let's use. I've used the left-hand rule because I'm more used to using the left-hand rule for the magnetic force. Okay. You can use the right hand, of course. So let's use the right hand. So the right hand, the first V is in this direction, but it has to be. That's a, that must be a mistake. So current field. I've made a mistake. The force is in the opposite direction, of course, because Q is negative. It's an electron, right? So this is an electron. So Q is -1. So it's in the opposite direction. It's embarrassing. Sorry. Doesn't change the calculation, but yeah. So it's moving in a circle. It's moving in a circle like this, and you can find the radius of the circle because you know the speed. So the radius equal to in the xy plane, the particle is moving in circles, and the radius is mass. So it's 9.11 times 10 to the minus 31. That's the mass of an electron, times the speed, which is 3√2 times 10 to the 6, divided by Q, which is 1.6 times 10 to the minus 19, times B, which is 0.2. So you can calculate that, and that's 911 to the power minus 31 times 3√2 times 10 to the 6 divided by 1.6 times 10 to the minus 19 divided by 0.2. Oh, that is not correct. No, it's time 3√2 times 10 to the 6 divided by 1.6 times 10 to the minus 19 and divided by 0.2. 1.2 times 10 to the 1.2 times 10 to the minus 4 meters, which is approximately 0.00 0.12 millimeters. So it's moving in a circle of radius 0.12 millimeters, and it's as I said, the particle in the z direction, the field has no effect because the force is 0. Therefore, the velocity in the z direction is constant. Okay, so that means if it's moving in a circle in the xy plane, but also moving up, what's the motion? What's the overall motion of the electron? Yeah, it is a spiral. It is a spiral. Yes. Spiral in 3D. So this is not using any math. So this is not what you're expected to do in this problem. Now let's use vectors. Okay. All right. So the velocity is going to be equal to Sorry. What's the best way to do it? Oh, you start from the. Okay. So we start by writing out this equation. F is equal to Q times V B. And we know that U has components in 3 dimensions, but that's the initial velocity. And B has only a vertical component. Okay, so we can write Fx, Fy, Fz, so the 3 components, is Q multiplied by the velocity, which we don't know because we only know the initial velocity, and times B. Well, we can, instead of velocity, we can say Vx, Vy, Vz multiplied by 0, 0, Bz. Let's keep it simple. Let's not substitute yet. Okay, that is the force. And from here, we can write down 3 equations. Fx is Q Vx. Oh no, what am I doing? Okay, let's multiply these. Let's multiply these 2 vectors. So that's equal to Q multiplied by the determinant of the matrix I, J, K multiplied by Vx, Vx, Vy, Vz, and 0, 0, Bz. You can see that's equal to Q open bracket. So I multiplied by the modulus of the determinant of this. So it's Vy, Bz minus J, which is Vx, Bz, and plus K multiplied by 0. You can see that this can be written as Q, well, Q Vy Bz, Q Vx Bz, and 0. So the force acting on the electron is equal to Q Vy Bz and Vx Bz and 0. Okay. Now F, velocity, is mass times acceleration. So mass times acceleration is equal to that. Q, well, let's just copy that. But acceleration is v dot is equal to m vx dot, vy dot, and vz dot. So you can write down from here that's mvx dot is vy bz, mvy dot is q vx bz, and mvz dot is equal to 0. If mvz dot is equal to 0, that means acceleration is 0. That means vz is constant. Okay, that's easy. So we'll be focusing on these two. Okay. Now we can integrate, I guess. So mvx, so that's dx dt. Oh no, sorry. M dvx dt equals vy bz, and m dvy dt is equal to q vx bz. Now if we integrate, we multiply by dt, m dvx equals q vy bz dt. We integrate, and similarly here, we'll integrate this bit, so there's going to be vx minus u, final minus initial, equals t. So that is just the integral of vy dt oh no, sorry. I don't think I can do this. I have to, okay. So from here, vy can be expressed as m divided by q bz dvx dt. And here vx can be expressed as m q bz dvy dt. Now, I substitute this into here, so I have to differentiate again. So dvx dt, I differentiate this part, is m q bz, and then dvy dt, so that's going to be d squared vy dt, that is dt squared, so that is m q bz multiplied by, well, yeah, let's keep it like that, squared, and we substitute that in. So vy is equal to m q bz multiplied by m q bz d squared vy dt squared. Okay. Now we just need to find vy. Sorry, let me just double check. Yeah, where's the minus coming from? I think I've lost a minus somewhere. I have, yes, of course. There's a minus here. And there's a minus here. There's a minus here. There's a minus here. And there's a minus here. So when I substitute that in, so m vx I express from here is going to be minus. Okay, so what I've written here is that vy Vy multiplied Vy, this thing, minus m over q bz squared multiplied by Vy double dot. This is the second derivative. And here I can express Vy double dot is minus q bz over m squared Vy. And this looks awfully familiar. Okay. What is the solution to this equation? Does anyone recognize the equation? Where's the chat? I've lost the chat. Oh, yes, thank you. Missed out the minus. Thank you for that. Yes. Oh, thank you. I didn't see the chat. Thank you for correcting me. There's a minus, so this is simple harmonic motion. So Vy can be expressed as q bz over m. No, sorry. Vy is A multiplied by cos omega t. Simple harmonic motion. Okay, and then we have this and similar Vx. Vx, as you can see, is what is the amplitude? Okay, Vx can be expressed through dy, so we need to differentiate dy. Vx is minus m qbz multiplied by a multiplied by omega, which is qbz over m, sine omega t, and this cancels. You get minus a sine omega t. And if you combine these, this actually is proof. If you combine them, that means Vx, Vy, and Vz is going to be the maximum. So it's going to be well, in the beginning, what we want to find the amplitude. Well, the amplitude is the maximum speed, so it's 3 root 2. Yeah. So that's 3 root 2 cos omega t, and omega is, well, bq omega t. I'll just keep it as omega t. Minus 3 root 2 sine omega t. Yeah, and that it means that velocity is the minus 3 root 2 sine omega t, 3 root 2 cos omega t, and just 3 times 10 to the minus 6. Sorry, I obviously messed up with the phase because the starting phase, it's not the t, but you can say that this is the initial velocity 3, 3, 3 plus that should work. Yeah, the initial velocity plus this. Sorry, I'll just keep it simple. Initial velocity. Okay. So how does that work with the initial velocity being that? Let me fix that. This is just one of the solutions, right? So technically, the solution must be like this: plus phi. So you add a starting phase, and then the initial velocity when t is 0, velocity is 3, 3, 3. So that's what you do. So that 3 Vx minus 3 root 2 sine omega t plus phi has to be equal to 3. And then this is 0, so sine phi has to be 3 divided by minus 3 root 2 minus 1 over root 2. So phi is either equal to minus pi over 4 or phi is minus 3 pi over 4. That's also acceptable. So cos 3 root 2 cos phi has to equal to 3 as well. And cos phi is 1 over root 2. So it's either phi is equal to pi over 4 or phi is equal to minus pi over 4. So this has to be this. So minus pi over 4. So answer. Velocity equals minus 3 root 2 sine omega t minus pi over 4, 3 root 2 cos omega t plus pi over 4, and 3. That's how the velocity changes. So obviously it moves in circles and then moves up. So a vertical spirals up. And then if you integrate that, you can find x. The r, the vector r is the integral of v with respect to time. So you can find the position as well. So you can find the equation of motion, and that would be also quite straightforward just to integrate this expression. So I hope that helps you to solve this question. It is a difficult question with 2 stars, but I've done it in 2 different methods. So I just used this common sense method, the A-level method, but then I actually used the proper method of using the components of vectors. All right. So then there's talk about the mass spectrometer and velocity selector. So here I'll just skim it through quite quickly. So a mass spectrometer is a device that allows you to Y for J component of V was pi because it's the same phi has to be the same. Sorry, minus. I meant minus, but it has to be the same phi. Otherwise, you get into trouble. Right. Yeah, sorry. I was in a hurry to finish it. That's why it's minus. A mass spectrometer is an ingenious device that allows you to calculate the masses of atoms to an astonishing number of cyclics. So if you look at the periodic table, so let's say gold, and element, and mass. So yeah, this is, I don't know if you've ever thought about it, but it's absolutely crazy because 1U is of course 1.67 times 10 to the minus 27 kilograms. So the mass spectrometer allows you to calculate the mass of an ion to correct to what, 10 to the minus 1, 2, 3, 4, 5, 32? 10 to the minus 32 kilograms. That's the accuracy of the mass spectrometer. Okay. Precision, sorry, the precision of the mass spectrometer. So yeah, how does it work? So we have an atom, an ion. So for example, a gold ion, which enters a magnetic field at a specified speed, at a given speed. The velocity has been selected by a velocity selector. So there's a velocity selector. So the speed is always the same for all ions. But then the magnetic field is a uniform magnetic field, and the radius of the path R1 and R2. So the radius can be given by the equation mv over bq. So we put some atoms of gold, we accelerate them, and then we put detectors, and we move a detector, moving detector. And depending on the position of the detector, we can determine the radius. And if we can determine the radius with the velocity known, q is usually 1, magnetic field known, we can find m. N is BQR divided by V, which is pretty cool. Okay. Mass, you can determine the mass of a particle, right? Does that make sense? Does that make sense on a scale of 0 to 10, please? By measuring the radius. Now, it's interesting how the velocity is selected, of course, because how do we actually make all the atoms to travel at the same velocity? Well, let's look at a simple velocity selector. City selector. And in a velocity selector, you have two fields. You have let's say a magnetic field into the page. B. And let's say we have a positive particle. That's an ion, gold ion, is traveling at velocity v. And of course, using left-hand rule, or okay, let's do properly. So the force is equal to qv times b, and the force can be found using the right-hand rule. So my first thing is velocity. So velocity. B is into the page, so the force is up. Force is up. It's like the grown-up version of the left-hand rule. But honestly, I only use the left-hand rule. I never use the right hand. So yeah. Velocity is if the force is up. So when the particle is inside the magnetic field, there's an upwards magnetic force. And it's equal to QVB. That means we can put charged plates on top and bottom. So we would put a positive plate on top and a negative plate on the bottom. And we can produce an electric field downwards. Electric field. So that means that the particle will experience a downwards force from the electric field. And the electric force, the electrostatic force, is QE. And E is, of course, E is the voltage divided by the distance or between the plates. So we can easily manipulate E. Now, in order for the particle to travel in a straight line, these two forces have to be balanced. And that means that QVB has to equal to QE. So Q cancels, interestingly. Yeah, so in a velocity selector, any particle will travel at the same speed. It doesn't matter what the charge is. And then the velocity is B over E. So, and then what you do is you put a wall with a very small, with a very narrow opening. So if the speed is too fast, it will be deflected more the electric field. So too fast will go like this, and it will hit the wall. Too fast. If it goes too slow, it will be deflected by the electric field down. Too slow. And if the velocity is just right, it will go through the velocity selector. Velocity is exactly B over E. So here's the velocity is greater than B over E. It will hit the wall. The velocity is less than B over E. You might be right. E over B, sorry. So many mistakes today. That's that's embarrassing. Yeah. Okay, so it's E over B. E over B. E over B. Velocity is less than E over B. So any particle that passes through the velocity selector will have the same speed. No, you can't divide two vectors. These are just moduluses. Velocity is, of course, this is the modulus of V. Yeah, no V. Here we just divide the modulus of E divided by modulus of V. That's what I mean when I don't write the vector symbol. I mean the moduluses. Now the Hall effect is a very interesting effect. So basically, if you have a conductor placed into a magnetic field, so let's say, yeah, so this is an electric conductor, and the current is flowing in that direction. So we can think of positive particles are moving in from left to right. This is the drift drift of the charge carriers. So charge carriers are moving from left to right. There's a magnetic field going into the page, so away from us. This is the magnetic field. And there's a force. There's a force, and it's equal to QVB. So of course, QV times B. Using the left-hand rule, so the current is to the right, the field is into the page. So that means that the force is that picture drawn inaccurately? Seems like it. I think we made a mistake with this diagram. But that's not the point. If you have the current, field, force. Anyway, so the charge carriers will experience a force. And the positive particles will be pushed up. Positive particles. There's a magnetic force pushing the positive particles up. That means that the positive particles will collect on the top side of the conductor, and the negative particles will collect on the bottom side of the conductor. And this means that you'll have a potential difference. If you connect a voltmeter on top and on bottom, it will register a potential difference. Now, if you take the potential difference is equal to the electric field multiplied by B, by the thickness, and that means, and the on any particle here. So, because these will have a magnetic force on the bottom, they will have an electric force on the at the bottom, downwards. The magnetic force has to equal to the electric force. So QVB has to equal to QE. So Q cancels. And that means that E is equal to the voltage divided by B. So VB is equal to voltage. This is the whole voltage divided by B. So the whole voltage is equal to BVB. Now, knowing the current in the wire, you can find the drift velocity. So drift velocity is, you can calculate it. B is just the thickness of the conductor. So what can you measure using this device? What do you think a whole meter measures? Whole meter. So a whole meter consists of a voltmeter and a strip of wire with given dimensions with a current inside. Whole meter. Whole sensor. So interesting. I never seen a Hall sensor like this, but yeah. I don't know exactly how it works, how this particular one works, but we can imagine that there must be a current. So let's say there's a current, and yeah, probably the current goes one way, so the current goes like this, and you place it into a magnetic field, and because of the magnetic field, there will be a potential difference on the top and on the bottom, and you measure it using the voltmeter. So you can connect the voltmeter here. The charge of an electron, no, not the charge of an electron, not the power. Look, the Hall voltage is the volt. So okay, does everyone understand why there is a Hall voltage? Why there is a Hall voltage? On a scale of 0 to 10, do you understand why a voltmeter placed here will register a voltage? Okay, good. On a scale of 10. Because the moving electrons experience a magnetic force, so the positive particles will be pushed up, and the negative particles will be pushed down. And because you have positive and negative, there will be a potential difference. Okay. This potential difference can be measured, and this potential difference is equal to B, which is the thickness of the wire. Drift velocity. This you can calculate that from the current, can't you? You can say, well, I equals NAEV. So you can work out V. V is the current divided by NAE. So V is something you know. What can we measure? The magnetic field. Yes. So this is a Hall meter measures the magnetic field. Measures the well, not the strength, but yeah. So a Hall meter, you place it into a magnetic field, and it tells you how many Tesla is that. Hall meter measures B by measuring the voltage. Okay, nice. Okay, you know that a current wire with current produces a magnetic field around it, and the equivalent of the Coulomb's law. So you know that if you take a charged particle of charge Q, the field E around a charge is equal to K Q over R squared. Okay, so that's the electric field. Okay, I won't put E. Now, the equivalent of the Coulomb's law is the Biot-Savart law. A small segment of wire, dl, carrying a current, I, produces a magnetic field, dB, at a given point. And that's the formula. So this small section of wire produces a small magnetic field, which is this. It might seem quite complicated. Now let me explain a few things. So I is current, of course. Mu0 is a constant for pi. Okay, easy. dl. dl is a vector. So just keep in mind that it has a direction. R hat. R hat is a unit vector in the direction of R. R hat is the unit vector in direction of R. And R is, well, the distance to a given point. So this is an arbitrary point in space. Okay. So if you take a long wire, you take a long wire carrying a current I, an infinitely long wire, and take a point at a distance A away from the, oh, let's not, yeah, A. Let's take a random section of the wire, dl. dl, that's a vector. And the vector r is going to be this. Okay. So the magnetic field from this section of the wire, dB, and of course we can find the direction. The direction is out of the page. dB is mu0 divided by 4 pi I, which is the current, which is given. Now dl multiplied by r divided by r squared. Well, we can certainly introduce an x. X is the position. This is the x-axis, and this is the position of x. So r squared is a squared plus x squared. That's useful. So it's going to be mu0 divided by 4 pi. And this I, we can take I out because that's known. That's a constant. That's going to be dl times r divided by a squared plus x squared. Now what is dl times r? Well, dl is a vector along the x-axis. So we can write dl is dx, a small increment in x, 0, 0. And r, well, it has components x, a, and 0 in the z. We can assume that it's flat. So let's find the product, dl times r, which is dx 0, 0, xa times xa 0. And this is I, j, k, dx 0, 0, xa 0. And that is I 0, j 0, and k multiplied by dx times a. So this vector is going to be 0, 0, a dx. Nice. So that's going to be I mu0 divided by 4 pi 1 over a squared plus x squared, 0, 0, a dx. So of course, that means bx is 0, by is 0, and bz is, well, is this. Well, dbz is equal to I mu 0 divided by 4 pi a dx divided by a squared plus x squared. And now we can integrate that for the whole wire. So we can, this is the field from a small section of the wire. And so now we can integrate that throughout the whole wire from minus infinity to plus infinity. And this is from 0 to b. And that means b, if we integrate that, that's simply b. And it's equal to, well, what can we do here? A is a constant. So it's I mu 0 divided by 4 pi times a. And then the integral of dx over x squared minus plus a squared from minus infinity to plus infinity. I have to look that up. I think it's arctan integral of 1 over x squared plus a squared. Okay, 1 over a, it's 1 over a I mu 0 a 4 pi, it's 1 over a arctan x over a between limits minus infinity and plus infinity. So arctan of infinity, that's pi over 2. So there's going to be I mu 0 a over 4 pi multiply 1 over a, and this is going to be pi over 2 minus pi over 2. So that's pi. Okay, so that's going to be a cancels. Pi over 2 plus pi over 2, that's pi. So pi cancels. So mu 0 I over 4. And I really hope I haven't messed up. What's the result for a straight wire? Mu 0 I divided by 2 pi r. 2 pi r. I have messed up somewhere. And I'm not sure where I went wrong. Somebody corrected me in the chat. R squared. No, I have. Where I haven't forgot R squared because R squared is a squared plus x squared. That was the point. 1926. Apologies. I mean the derivation is here. It's a slightly different derivation. I'm not sure what went wrong. But this is the correct derivation. This is in the assignment. I was just showing you how this can be done. Apologies for getting it wrong. But yeah, it's going to be mu0I divided by 2 pi r, and I got mu0I divided by 4. So obviously something went wrong. 2 pi r. So yeah, it's wrong. Okay, but that's the point. You take the field from every single part, or every single small wire, and you find the magnetic field, and then you add all these magnetic fields. Okay. Magnetic field of a long wire, wire carrying current. So let's see how it's can be done. A wire carrying current of 0.1. Now calculate the magnetic field distance of 0.5 meters from the wire. Well, that's very straightforward. So the current is 0.1 amps, and you are at a distance of 0.5 meters. The magnetic field at this point is mu0 I divided by 2 pi r, which is mu0 times 0.1 divided by 2 times pi times 0.5 meters. Okay, and then you just substitute that in. Mu0 is, where's mu0? The constant 33. Times 0.1 divided by 2 divided by pi divided by 0.5. 4 times 10. 4 times 10 to the minus 8 Tesla. That's it. Now, unfortunately, I don't have time to go through, but these are quite simple. Problem 7. And problem 8 just talks about loops, right? So when you're talking about a loop, so you are at the center, you need to find B at the center, and you have different sections of the wire, DL. They all contribute to the field at the center of the loop. So the field at the center of the loop is going to be the strongest. And here's the formula that allows you to calculate the field at any point along the axis of the loop. Along the axis, that is, the derivation is given in the assignment. But yeah. So yes, thank you for your attention. I hope it was somewhat useful. Please do watch my other webinars if you're still confused, or better watch the derivations that are, the links are given in the assignments. All right, you're welcome. I'll see you. When's the next webinar? I think it's next week, actually. Year 13 webinars. Yes, differential equations is next week. Okay, see you everyone. Bye.